Chapter 6 is on radical expressions, radical equations, and radical functions. And it's a big chapter. In fact, there are 8 parts to that. And number 6.1 is radical expressions and functions. Then 6.2, rational numbers as exponents, and then simplifying radical expressions, and then addition, subtraction, and more multiplication of radical expressions. And then we have the on division of radical expressions. Then we solve radical equations and applications involving powers and roots. And then last but not least, complex numbers. It's probably a new field for most of you, the complex numbers. So let's focus on section 6.1. And so here we have 4 objectives. Number 1, to find the principal square roots of numbers and their opposites, and then approximate square roots, identifying radicals, find outputs of square root functions, graphing square root functions, and then finding the domains of square root functions. And then we learn how to simplify radical expressions with perfect square radicands. And then we find cube roots and simplifying certain expressions and finding outputs of cube root functions. And then we simplify expressions involving odd roots and even roots. So that's section 6.1. Let's go into the details. So square roots and square root functions. First, let's define the square root. And we say the number c is a square root of a if c squared equals a. And for some simple examples, 5 is a square root of 25 because 5 squared, or 5 times 5, equals 25. But notice that minus 5 is also a square root of 25 because minus 5 parentheses squared means minus 5 times minus 5. And since minus times minus is plus, it's also equal to 25. Now the number minus 4 does not have a real number square root because there is no real number c such that c squared equals minus 4. So then we have some properties of square roots, and that is that every positive real number has 2 real number square roots, and the number 0 just has 1 square root, 0 itself, and then negative numbers do not have real number square roots. Later on in section 6.8 we'll modify that somewhat, but right now, for the time being, negative numbers do not have real number square roots. I mean, the real number part is still applicable in any case. So then we're going to talk about the principal square root, and we'll be dealing a lot with the principal square root. So the principal square root of a non-negative number is its non-negative square root. And the symbol, like this with an A, represents the principal square root of A. And to name the negative square root of A, we can write minus square root of A. So some simple exercises. So the square roots of 9, of number 1, 9, is 3 because 3 times 3 is equal to 9. But minus 3 is the other one, minus 3, because minus 3 times minus 3 is also 9. So we have 2 roots here. And for number 2, it's 36. So the square roots are 6, because 6 times 6 equals 36. And minus 6 is another one, because minus 6 times minus 6 is also equal to 36. And then we look at number 3, 121. 1 square root is 11 because (11) times 11 equals 121. And minus 11 is the other one because minus 11 times minus 11 is also equal to 121. So for 4a, the principal square root of 16 is 4, because 4 times 4 is 16. And the negative principal square root of a is minus 4. And the square root of a negative number is not a real number. Okay, now let's look at number 5. So the principal square root of 49 is 7. And the negative square root of 49 is minus 7. And the square root of minus 49 is not a real number. And of course, the square root of 1 is equal to 1. And the negative square root of 36 would be minus 6. Again, the minus comes from in front of the radical symbol. And here, the square root of 81 divided by 100, we can rewrite that as the square root of 9 squared divided by 10 squared. So it'd be equal to 9 divided by 10. So that's 9 divided by 10. And this is simply equal to 0.08, because when you square 0.08, you get 0.0064. And number 10, the square root of 25 is 5. Of course, with a minus sign, because there's a minus sign here. So minus 5 divided by 8. Because 5/8 squared is equal to 25/64. And here, that's equal to the square root of 16 is 4, and the square root of 9 is 3, so that equals 4/3. And for number 12 is minus 0.9, because when we square 0.9, we get 0.81, and then with a minus sign. So it's minus 0.9. And the square root of 1.44 is simply equal to 1.2. If you square 1.2, you get 1.44. The next 4 exercises ask us to approximate the square root to 3 decimal places. And if you have an iPhone, or probably an Android, works the same way. When you hold your calculator in landscape mode, then you see that there's a square root function. I'm going to point it out with a pen. Here's the square root function. It's hard to get a focus on that. But anyway, there you see it. There you see the square root function. Right here. Okay. Here's the square root key. So you input a number like 17 and then touch this key and then the answer will appear. So I will do that. 17 and then square root of 17, and here's the result, 4.123. And since we are having 3 decimal places, so the approximation would be 4.123. So that's approximately equal to 4.123. Similarly, the square root of 1,138 is equal to 33, approximately equal to 33.734. And the square root of a negative principal root of 867.6, 867.6 square root. That would be minus, so it's approximately equal to minus 29.455. Oops. We're going to write underneath. So minus approximately equal to minus 29.455. This was 4.13. This was 33.734. And so for this one, we divide 22 by 35. And then take the square root, and that is equal to approximately equal to 0.793. Next, we have a little bit of vocabulary here. This symbol is called a radical. The radical symbol, and the expression with a radical is called a radical expression. So anything with a symbol is called a radical expression, and the expression written under the radical is called the radicand. So these are important terms that you need to remember, that this is called a radical, and then an expression written with a radical symbol is called a radical expression, and the expression that's underneath the radical is called the radicand. We use that quite frequently. So here we are asked to identify the radicand. Of course, that's the expression under the radical symbol. And so the radicand is 28 plus x. That is the radicand. 28 plus x. For number 19, the radicand is y divided by y plus 3. That is the radicand. In the guided solution exercise, we have a radical function, g of x equals the square root of 6x plus 4, and we are supposed to evaluate this function for x equals 0, x equals 3, and x equals negative 5. So what it means, g of 0, we replace x with 0, so it becomes 6 times 0 plus 4. And of course 6 times 0 is 0. So we only have the radical, or the square root of 4. which is equal to 2. So that's what g of 0 is. So g of 0 equals 2. Now g of 3 means we replace x with the number 3, so 6 times 3 plus 4, or 18 plus 4, which is the square root of 18 plus 4 is 22. So that's g of 3, square root of 22. For g of negative 5, we replace x with the number minus 5. And so we get 6 times minus 5. And that's equal to minus 30. And minus 30 plus 4 is minus 26. And there's no real number function for that value that exists. So minus 26 is a negative radicand. It's a negative radicand. And no real number function value exists for this value of x minus g of minus 5, x equals minus 5. For number 21, we are evaluating the function f of x equals minus square root of x. For x equals 4, x equals 7, and x equals minus 3. So then f of 4 simply means minus the square root of 4, which is equal to minus 2. And f of 7 is equal to minus the square root of 7, and that's equal to minus 2.646. Well, approximately equal. Minus 2.646. And then when we replace x with the number minus 3, so f of minus 3 is equal to minus the square root of minus 3, and does not exist as a real number. Does not exist as a real number. As a real number. Sorry about the writing. But you get the idea. Because the square root of a negative number is not a real number. So for number 22, we're asked to find the domain for each function, well, for 22 and 23. So let's say number 22. So we know that the radicand for a square root has to be greater than or equal to 0. And the radicand, of course, is x minus 5. So that has to be greater than or equal to 0. So we have a linear inequality. And when we add 5 to both sides, then we find that x has to be greater than or equal to 5. And in set notation, the set of all x, such that x is greater than or equal to 5. And in interval notation, it would be the interval from 5 to positive infinity. And for number 23, again, we know for the square root to exist, the radicand for number 23 is 2x plus 3. 2x plus 3. And so that has to be greater than or equal to 0. So again, that's a linear inequality, and we solve it by subtracting 3 on both sides and dividing by 2. So x is greater than or equal to minus 3/2. So the solution, in set notation, the solution of the domain is a set of all x such that x is greater than or equal to minus 3/2. And in interval notation would be the interval from minus 3/2 to positive infinity. The next exercise is to graph the function, the radical function f of x equals 2 times the square root of x plus 3. And so first of all, let's determine the domain of that function. So the domain of the function means that x plus 3 has to be greater than or equal to 0, or x has to be greater than or equal to negative 3. So the domain is from minus 3 to a positive infinity. Okay. Now let's make a table of values. We can choose x to equal 0. Then f of x is equal to 2 times the square root of 3. And 2 times the square root of 3 is approximately 3.46. So we have the ordered pair 0, 3.46. Then we can let x equals negative 3. Then that means that the radicand is minus 3 plus 3 is 0. 2 times 0 is 0. So then we have minus 3, 0. And we can let x equal 6. Then we have x plus 6 plus 3 is 9. And the square root of 9 is 3. And then 2 times 3 is 6. So there would be 6, 6. And when we plot these values, these ordered pairs, so now we've plotted the ordered pairs minus 3, 0, 0, 3.46, and the point 6, 6. And now we can connect or draw a smooth line through these 3 points. And this is a graph of the function f of x equals 2 times square root of x plus 3. The arrow indicating that the line continues indefinitely to the right. Finding the principal square root of a squared. Simplifying square root of a squared. When a is greater than or equal to 0, then the square root of a squared is equal to a. And if a is positive or 0, the principal square root of a squared is a. And if a is less than 0, then the square root of a squared is equal to negative a. So in other words, if a is negative, the principal square root of a squared is the opposite of a. So now we talk about the principal square root of a squared. For any real number a, the principal square root of a squared is the absolute value of a. In other words, the principal non-negative square root of a squared is the absolute value of a. So let's do some exercises, and they're really simple. We look at number 26. So the square root of y squared would be the absolute value of y. The absolute value of minus 24 squared would be 24. The square root of principal square root of 5y parentheses squared is 5 absolute value of 5 times the absolute value of y. And the principal square root of 16y squared is 4 times the absolute value of y. And the principal square root of x plus 7 quantity squared is x plus 7, absolute value of x plus 7. Here we have the principal square root of 4 times x minus 2 squared. So the principal square root of 4 is 2. And then the absolute value of x minus 2. Similarly here, the principal square root of 49 is 7. And then absolute value of y plus 5. Sorry about that. So the absolute value of, the principal square root of x plus 7 squared is the absolute value of x plus 7. And here it's the absolute value of the square root of 4 is 2. And then the absolute value of x minus 2. And here the square root of 49 is 7 times the absolute value of y plus 5. In the guided solution, it's very similar. We can factor x squared minus 6x plus 9 as x minus 3 squared. So then the principal square would be absolute value of x minus 3. Next, we'll be covering the topic of cube roots. And so the cube root is as follows. The number c is a cube root of a written the third root of a if the third power of c is a. That is, if c to the third power equals a, then the third root of a equals c. So here's some simple exercises. And when you look at number 34, so the third root of minus 64 would be minus 4, because minus 4 to the third power is equal to minus 64. And here the third root of 27, y to the third, we can write that as the third root of 3y to the third power. So in other words, that would be equal to 3y. And in number 36, we can rewrite that as the third root of 2 to the third, x plus 2 to the third. So that would be equal to 2 times x plus 2. And number 37, we can write that as the third root of minus 7/4 to the third power. So that means that's equal to minus 7/4. Seven to the third power is 343. And so that would be the answer for number 37. And in number 38, we are asked to evaluate a function. It has a cube root here. So g of minus 23, so that means we replace x with minus 23. So that, in other words, would be the third root of minus 23 minus 4. And there would be the third root of minus 27, which is equal to negative 3. And g of 4 means we replace x with the number 4 in this expression. So third root of 4 minus 4, which is the third root of 0, and that is equal to 0. And g of minus 1 would be g of minus 1. Replace x with minus 1. So we have the third root of minus 1 minus 4. Minus 1 minus 4. And that would be the third root of negative 5. And we can evaluate that, and again your calculator has the third root, the cube root, so it's about minus 1.710 approximately. And then for the last part, g of 11, we get third root of 11 minus 4, and it would be the third root of 7, the cube root of 7, and that is approximately equal to 1.913. Again, your calculator will give you the correct answer. Now we're going to talk about odd and even kth roots. So in the expression the kth root of a, we call k the index and assume that k is greater than or equal to 2. So the word index is an important vocabulary word in the context of radical expressions. So the index is that number that's written in this place here. For example, the fifth root of a number a is a number for which number c for which c to the fifth equals a. There are also seventh roots and ninth roots and so on. So whenever the number k in the radical, with a k in the index k is an odd number, we say we are taking an odd root. So here is the rule. If k is an odd natural number, then for any real number a, the kth root of a to the k is equal to a. Very important identity to remember. Find each of the following. So for number 39, the fifth root of 243, well, we can write 243 as 3 to the fifth power. So we know that from the previous definition that that's equal to 3. That's for number 39. So 3, the fifth root of 3 to the fifth is 3. Similarly, the fifth root of minus 243 would be the square root, the fifth root of minus 3 to the fifth power. And we know that that's equal to minus 3. And the fifth root of x to the fifth is simply x. And the seventh root of y to the seventh is simply y. And the fifth root of 0 is 0, because we can write 0 to the fifth power, and then It all matches with the previous definition of the kth root of a to the k. And so here we can write this as minus 2x to the fifth power. And so we have the fifth root of that expression. So we know that that's equal to minus 2x. So here the radicand is the expression 3x plus 2 raised to the seventh power, and we're talking about the seventh root, so that would be equal to 3x plus 2. Because the power is the same as the index. Here are two important observations about simplifying radical expressions. For any real number a, the kth root of a to the k is equal to the absolute value of a when k is an even natural number. And we use absolute value when k is even unless a is non-negative. So if we know that, we don't need the absolute value symbol. This is going to be pretty important, as you will see in a moment. And the kth root of a to the k equals a when k is an odd natural number, is greater than 1. We do not use absolute value when k is odd. So keep those two things in mind. So here's some exercises. Find each of the following. Assume that letters can represent any real number. That means positive or negative. So the fourth root of 81, that would be the same as the fourth root of 3 to the fourth power. So that's equal to 3. And minus the fourth root of 81 is equal to minus the fourth root of 3 to the fourth. So it will be equal to minus 3. Now, the fourth root of minus 81 does not exist as a real number, so not a real number because the even root of a negative number does not exist as a real number. And the fourth root of 0, of course, is 0. And for number 50, we can rewrite this as the fourth root of 2 times x minus 2 to the fourth power, and that then becomes 2 times absolute value x minus 2. Because obviously 2 is a positive number anyway, or a non-negative number anyway, so we only need to put the expression x minus 2 in absolute value between absolute value symbols. And so that is simply absolute value of x. Again, we are told that x, the letters can represent any real number, so it means it could be a negative number, and therefore we need to use absolute value symbol to make sure it's a positive value, or non-negative value, I should say. And then for number 52, let's look at that. The eighth root of x plus 3 to the eighth power. So there would simply be x plus 3 absolute value symbol. Absolute value of x plus 3. That would be a solution for number 52. And here we have an odd root. So here the solution is simply x plus 3. as it was said above, we don't use absolute value symbols when we have an odd index. And now for the last exercise, we have the fifth root of x to the fifth, or 243 times x to the fifth. So we can rewrite this as the fifth root of 3x to the fifth, and that's equal to 3x. Again, we don't need absolute value symbols here because we have an odd root. And this concludes section 6.1.